Hello, Danny. Do you know the IMF of blood? Let us show you, Dan.
Blood is made up of several organic compounds. The majority of it is made of plasma, which contains a lot of water as well as salts, proteins, glucose, and more. Inside of that plasma, there is hydrogen bonding between the water molecules as well as ionic bonding between the salts. In the red and white blood cells, the plasma membrane is made of lipids with head groups and hydrophobic tails. When put together, the lipids form fatty acid chains that are held together by London dispersion force and helps the cells stay together under high temperatures. This is also dipole-dipole interactions between the polar head groups and the water around it.
Hi, Lloyd. Bit slow tonight, eh?
Yes, it is, Mr. Torrance. What will it be?
Well, I'm glad you asked, because I myself could use a little bourbon, a little glass and some ice. You can do that, can't you, Lloyd? You're not too busy, are you, Lloyd?
No, sir. Not busy at all.
Good man, Lloyd. Good man.
While we're discussing, do you happen to know the chemical composition of ethanol?
No, I do not, but I would really like to. I really would.
Drink up, Mr. Torrance. Well, ethanol is the alcohol present in alcoholic beverages, such as your bourbon here. It contains 2 hydrogen, 6 carbon, and 1 oxygen atom, giving it a chemical formula of C2H12OH. As you can see, it contains 1 methyl group, CH3, 1 methylene group, CH2, and 1 hydroxyl group, OH. As for its molecular geometry, it contains 2 tetrahedral structures around the carbons and a bent structure around the oxygen. When you ingest ethanol, it dissolves and passes from your digestive system to your bloodstream. From there, it travels to your brain, where it increases dopamine production and latches onto nerve receptors to slow down brain function. It does this by decreasing products of glutamine and increasing the production of gamma-atropuric acid. This one makes you feel drunk.
Thank you, Lloyd. Thank you. How do you like it? You said we were gonna do a lab on energy transfers.
What? I don't even know what they are.
Well, allow me to show you. Give me the ring stand.
No!
I need it to show you energy transfer.
Stay away from me!
When, dark light of my life, you didn't let me finish. I was telling you about energy transfers. You see, energy can't be created or destroyed. It just transfers into a different type of energy. This is happening constantly all around us. For example, the Bunsen burner takes the chemical energy of the gas and turns it into thermal energy when the gas is ignited. When you put something over the flame to heat it, that thermal energy is transferred into kinetic energy. As it excites the molecules in the substance, it heats up. Something similar happens when you plug in the lamp. The electrical energy from the plug turns into light energy, while also producing thermal energy inside the bulb. Don't you understand? Now give me the ring stand, Wendy. Wendy, do you know about gas laws? Open the door, Wendy, and I'll tell you about them. No? Then I'll huff, and I'll puff, and I'll explain them to you. There are several different gas laws, written by Boyle, Avogadro, Charles, Gay-Lussig, and Dalton. Boyle's law states that pressure is proportional to volume. This means as pressure increases, volume increases. Avogadro's law states that gases with equal volumes have the same number of particles. Charles' law states that when volume increases, temperature increases. Gay-Lussig's law states that as pressure increases, temperature increases. There is a combined gas equation that puts all those laws together into one equation. This only works when the gases are ideal. You see these laws in place when your tire feels flat, when in cold temperatures, or when a soda can explodes when it's hot outside. Those are some of the gas laws. Here's Johnny!
Wow, you dead. You must be dying because it's so cold in this here recital hall.
Never mind that. Look at all this snow. Have you ever wondered why snow is solid? First, the atmosphere which reach a temperature at or below 0 degrees Celsius. These temperatures cause the water droplets in clouds to be solid rather than liquid. The heat in the water molecules that make up the droplets is transferred out of them as the temperature decreases. The molecules then begin to move slower and slower until they have lost so much kinetic energy that they freeze and become a solid. These ice crystals are then dropped to the ground and they become heavy, when they become too heavy, giving us the snow we know and love. This is an example of phase change in a real-life scenario.
In order for the snow to stick and become deep like it is here, the temperature in the area the snow falls must also be below 0 degrees Celsius. If there were to be a temperature above this, thermal energy would be transferred back into the water molecules, exciting them and bringing them back to their liquid.
Cool! Red rum, red rum, red rum.